And then do I, oh, something's working. So then I share screen from here?
Yep. Perfect, cool.
Which is where?
It's that green.
Now what's the green?
Yeah.
Yep. It's obvious.
Wrong slides. I think this is it. I'm going to make one small.
Oh yeah, I have it on.
All right, just one goes here. Don't have
Oh, I thought that guy was kind of sitting in. Thank you. Yeah. All right, welcome everybody to Orchestructure. We meet the second to the last Wednesday every month?
Last Wednesday.
Last Wednesday every month? Is that the day? You're mixing it up with I am. I'll be your host today, George Castro. Mario has a family emergency, so he can't make it. So welcome to the 1-year anniversary of Orchestructure's day. So make sure you get a sticker if someone's holding on. We actually have like a new design. It's the O, the period on it. When something subtle, we get plastic. Put that on your work laptop and not get fired. We still want to do a workshop for the summer, which is basically we put on a bunch of classes for people who don't know certain topics, getting started with containers, all that kind of stuff. So we do want a date for that. We haven't really quite settled on a date, so we had to bump the date that we originally wanted to. So if you could vote on the dates, where do we vote?
It's in Slack.
Okay, just go to the Slack channel, let us know what dates work for you. Also, this is, Bob is running a survey that he'll toss the link in Orchestructure on the Slack channel. I forgot what the survey was.
The survey is for the workshop itself and what people actually want.
There we go. Okay, that's good to know. Because I've also read that 3 times and forgot. And next month will be Vault presentation at Ithaca, which is down that. Awesome. So that should be a very popular talk, so you might want to get there a little bit early. Other than that, anyone have any announcements or anything they want to say?
You did good.
All right, I'm not fired. Awesome. All right, take it away.
Take it away. Thanks everyone for coming. I'm in Vielmetti. I work here at Work and Tile, which is a co-working space. And I was asking about co-working. I also work at Packet, which is a bare metal cloud provider based in New York. Get out there about once a year. Mostly work here or from home or coffee shops or what have you. The project I'm working for has some stickers on the table, of course. It's called Works on ARM. It's basically a project funded by ARM to do software enablement and open source system development on ARM systems. There's no package branding to speak of on this talk. There's not really any ARM branding to speak of on this talk. And I use some logos that probably wouldn't fit in an ARM-funded talk. So let me just get started. So the outline, a little bit of computer history, some of the recent past, basically my last 18 months worth of working on ARM systems, some sense for the state of the art for ARM in the data center and ARM in general, and a brief look at the future with my prognosticator hat. Oops. So why is ARM interesting? Well, change comes from below. Once upon a time, mainframes roamed the land, and then many computers came along and stopped the mainframe growth. Many computers in turn were displaced by workstations. Workstations in turn were displaced by PCs, even though people thought the PCs were horrible, slow, crummy, very hard to use, just toys. They ended up wiping out the workstation world. And the part of the thesis of why ARM matters, why you would even care, is the thought that the PC generation will be displaced by the cell phone generation. that the process of building cell phones in quantity, in such enormous quantities, has meant that those phones and the chips that are derived from those phones have established a process parity and then a process improvement upon Intel, and it's just like the next wave of things. Now, Intel would take exception to this in the data center. They're right because they have like 99% of the market. But if you think of this, of things happening in waves, it's entirely plausible that 5 years from now, ARM systems in the data center are ordinary rather than special snowflakes. Just slow, just entirely based on how many ARM-based chips are. So if you turn the Wayback Machine to 1985, you get a prototype board. Steve Ferber and Sophie Wilson are the engineers. Took them about 18 months to build a chip. They visited the people who made 6502, MOS technology, saw how few people were in their facilities, saw how relatively easy it was to design a chip. They had a very low power budget, and the first chip that they designed was so low powered that it still worked even if you didn't apply power to it, because it could draw from the diodes on the I/O lines, and that was just enough power to keep it running. So, so basically, imagine a chip that was designed from the very start to be power efficient, and that becomes a big part of the whole story along the whole thing. By 1992, 7 years later, the system here is the Acorn Archimedes A3020. No one in this country grew up with one of these things unless they moved here from the UK, right? Because these were like school computers in Britain. The chip is an ARM 250. It's 32 bits at 12 megahertz. It runs RISC OS. It's fine, but it didn't ever get worldwide appeal. So the first system that people probably have heard of, I hope you can read this. If you weren't around for Doonesbury in 1993, there was a series of scripts, Michael Doonesbury using his brand new PDA, the Apple Newton. And the Apple Newton was this revolutionary handwriting recognizing thing that didn't do a very good job of recognizing it. And so it was a big flop to a big degree. Yet this was also ARM powered. And what you see going forward is that by the year 2000, the dumb phones, which were powered by ARM-based chips, and the smartphones that are started to become powered by ARM-based chips, become ubiquitous in the cell phone industry. And the key thing to know about ARM, they went through a couple of gyrations of ownership and management and whatnot, but the key thing to understand about their business model is they don't really make chips. They make intellectual property, designs for chips. And then the chips get made by dozens or hundreds of different silicon manufacturers. So come on through if you need to. I don't want to stop you. If you're interested, you can stick around. So in this world, it's not one silicon foundry selling you a small range of products. It's an IP vendor selling to all comers who make all kinds of crazy stuff, but mostly designed in this world. They've moved away from, in the intervening time, the cell phone is the driving factor. And by 2007, the iPhone 1, that's an iPhone 1 screen, is powered by an ARM 11 CPU. ARM doesn't, unlike Intel, which has a chip that runs the same exact everything that you can still run old code on the new one, ARM made a series of designs that were similar to each other, but you still had to rebuild for each one. So this is, the iPhone 1 is an ARM 11 CPU. I think it's an ARM piece. A 90 nanometer process. By 2005, they had 98% of the mobile market share. Just incredible amounts of people doing things with this design. Here's where it gets interesting and starts to get into the computer world rather than the phone world. So the Raspberry Pi from 2012 is a design that reuses parts, essentially reuses parts from the cell phone world. So it's the first real time that cell phone derived stuff becomes readily available to people hacking on it. And over the span of 6 years, they sell 19 million of these things, including 2 in this room right now that are the door controllers for our doors. I first ran into the Raspberry Pi a couple years after it came out. We were doing a control system for a solar energy farm at Firekeepers Casino in Battle Creek. A bunch of great big solar tracking arrays that follow the sun because they're programmed to turn motors that follow them. You wouldn't want to run an industrial motor on a Pi, but you could send the industrial controller the right coordinates from the Pi, and that's what we did. And so we had a Raspberry Pi in the middle of a field in a little hut, controlling, essentially being the brains, not really the brawn, but the brains behind a solar farm. At $35, it was easy, as an easy decision. The other part that we had thought about was the digiboard part, which was a bigger motherboard that had half the memory, even half the memory back then. Slower processor, I/O that we couldn't use, a bunch of other stuff. So it's not surprising that the Pi opened up a market for ARM in the computer world as opposed to the phone world. And this is the recent past for me. So back in 2016 in the fall, I got a note from a friend of mine in Germany, Dieter Reuter, who works on the Hypriot project. Hypriot is doing Raspberry Pi-based operating system based on Debian, designed for container use. So when it boots, it has Docker already installed. It has a couple of other things in it. Dieter wrote me a message late one night on Twitter, late my night, probably early this morning, saying, hey, you need to check out these guys at Packet. They had this top secret 96-core ARM server. And I'm thinking, 96 cores is a lot more than 4 cores. 2 gigahertz processor is a lot faster than the 1 point whatever gigahertz processor is at. It had 128 gigabytes of memory, which is an interesting amount of memory, and a fast network chip. And this is sort of how I got started on ARM within this hour. I got an account at Packet. They had a little beta test program. I signed up. First day, compile Go. It worked. Okay, compile Docker. I didn't quite work. Okay, file a bug. Right? And if you approach the world of open source software 18 months ago, and you are on ARM systems, and you were looking to open bug reports, you could open up a bug report every couple hours. There were that many small things that were wrong. That diligent use of make my chain 96, so you can use all the cores, and then make test. There would almost always be something wrong. Fortunately, this was a fast enough machine to still be interesting to find something wrong. So that was how I got my go on it. Since 2016, things have gotten better. Anyone in this room who uses these things regularly knows that they're not perfect yet, but they've gotten better. 18 months ago, Ubuntu was basically the only thing you could run on these systems. Now we've got Ubuntu, Debian, CentOS, Fedora, RHEL with an asterisk because of licensing issues. We're working on SUSE and OpenSUSE, and we've got a FreeBSD port that's good finished up. Software has gotten better in the sense that over the span of 18 months, enough people have opened up enough bug reports that are easy to fix, that they have generally been fixed. And the bugs are mostly squashed. The interesting thing has been, now that everything sort of works, and by everything I mean most things, people are looking at performance, because the pitch for these ARM servers is that they're low power and they're efficient. Well, low power and efficient doesn't really make excel if your software is not. Because they're efficient when the codes are actually running on optimized code. And if you haven't written the assembly language that gets your crypto working at line rate, it's not a very interesting system. So this graphic here, it's kind of hard to read because it was kind of a crummy photo to begin with, but it shows Cloudflare. Cloudflare does global scale web CDN, right? And they did a head-to-head comparison between Intel Xeon and Qualcomm Centriq. Centriq is the latest addition from Qualcomm. Qualcomm makes a bunch of cell phone chips, and they have ambitions to. They hate Intel as a matter of corporate strategy and policy, and so they've attacked Intel in the data center. And the watt meter shows that a Intel Xeon system on Cloudflare's workload, running at about 235 watts, has an equivalent throughput to the same workload, again, it's Cloudflare's workload, which the Centriq runs at about 150 watts. And if you're deploying lots and lots of machines, and if you control all your software stack, and if everything lines up in the right direction, you can save a third on power, which means you're saving a third on power and at least a third on cooling. And your things are probably going to run a little bit longer because they're not as hot. And a whole bunch of other good stuff happens. What are people actually using these systems for? At Packet, the first best use is build machines, just making software, right? Either making software for the next generation of stuff, just to make sure it works, or making software for embedded systems, where you're running a workload, instead of doing it emulated, you're doing it. And emulation is slow. It's like, runs at like 10 to 20% of native speed. So if you're building for ARMv8, on an ARMv8 machine, it runs a lot faster than building on Intel. And Cloudflare's workload, Cloudflare is really the first company to say publicly that our software works as well. They're not saying it's faster. They're saying it's as good for lower cost of operation. It's a different story, right? It's not like we have the hottest chip. It's not like we have the fastest chip. It's like, well, it's good enough, right? But it'll run at a less expense. So what has been 18 months worth of effort? Firmware and network drivers. Anyone dealing with booting systems that haven't been booted millions and millions of times before finds out that firmware is the first enemy. It's not your friend generally. Things like IPMI, dealing with DHCP, dealing with Pixie, boot, just all sorts of stuff that doesn't get exercised very well and that the firmware writers themselves don't understand very well. Sometimes not very well standardized, gets in the way. I work on a lot of operating systems, either operating systems directly building or people building large farms of packages like package managers. Lots of work getting languages and libraries to work, just because it works. It's really necessary to have a compiler that you can trust, and even more necessary to have a compiler that generates fast code. Obviously, containers and orchestration are a big deal because you want to look at something like a Docker Hub as a package repository that you want code from. We talked to the folks here in this room who are doing big data and scientific computation. My personal workload at Packet is not completely lined up with that, but it's important to take advantage of those issues. And then what we're really looking at is web scale data management tools, things like CDNs, things like global name service, things like global routing, where the end story is not equipment in 4 data centers or equipment in 1 data center, but really equipment in hundreds of data centers. Aspirational goals, right? You want to have your travel plans to go fix a server at a remote data center if the remote data center is somewhere interesting. So get your passport ready. What's fun about a system like this? This is a Thunder X2, which is a Cavium's next generation system. It exposes 224 threads to the operating system, which means that H-top is really fun to look at because you never run out of cores. It's like you have too many cores sometimes. You know, so this thing is only, I don't know if you can see it, but it's only running at a load average of 87. That's just idle. And for people who are used to 4-core, 8-core, even 24-core systems, this is impossibly many. And as it turns out, parallelism, parallelism is hard because of something known as Amdahl's law. Gene Amdahl was a mainframe designer, and he observed back in the 60s, 70s, that you could parallelize processes all you want, but even if you have all of the parallel work going on in 0 time, there's still some serial effort that needs to go on where something depends on something else, and a parallel machine doesn't speed that up. And we've seen that with these very high core count systems. Parallel processing only goes so far. Like the stereotypical problem is the compiler. It compiles really fast. It compiles all your .c's and .o's at the same time. And then there's a linker step, and the linker step takes forever. So it's running at So there's not enough people who've used systems with lots of cores yet for people to get, you know, just easy familiarity with it. I'm trying to fix that, but it still takes time for people to adjust to it. So one portability story is Go programming language. Go is super important for orchestrated systems. All of Kubernetes is written in it, all of Docker is written in it. Most of the ancillary programs that support Docker and Kubernetes are written in Go, or Go is the first choice for that. So I've been working on Go. This is like the 5th release of Go that I've had my mitts on in some way. With Go 1.7, it had an amazing little bug that if you did the system get page size call, it would always record 64K, even if the hardware you were on had 4K pages. Now, why did that happen? I lost and missed the time. I'm sure there's a good reason for it. But the impact of it is that Docker had an optimization routine that tried to be really clever about packing things into page size boundaries in a file system. And so if you had a file system that was really deeply nested, like 40 layers deep, 50 layers deep, it would crash at layer about 43. Now this is not something that you find you type in a command that doesn't work test. This took a little bit of debugging to sort of figure it out. And then a little more debugging to write the Docker file that would routinely crash. It's a Docker file that just says, basically, it's a series of directory commands, 100 deep. And if you can make a file system 100 deep, you're safe. So there was a bug in Go. By Go 1.8, that bug was fixed, but that wasn't really the end fix because Go didn't have a binary distribution for ARM64. So if you wanted to build Docker from scratch, you also had to build Go from scratch. And building things from scratch is not very much fun if everyone else has binaries. So by 1.9, we had given some hardware to the Google folks to do their builds on. They got it integrated in their build system, and they released binaries, which was a tremendous win. And then, since binaries were released, more people could test stuff, and we noticed that the performance was slow on some particular routines that got used a lot in crypto. Go 1.10, because the Go developers had these systems with a zillion cores and noticed that they weren't in use all the time, therefore the compiles took too long, they improved their compile times by parallelizing more parts of the build process. But the crypto routines were still slow, and a bunch of other stuff was still slow. And the folks at Cloudflare did a blog post with their brand new, hot, really fancy Qualcomm hardware, and said basically, this is awesome hardware, except your Go compiler sucks on ARM64. And they had all the numbers and all the charts and all the workload and everything to prove to people who I aren't told, but to other people, that the system wasn't quite ready. And this lit a fire under Qualcomm, under ARM, basically any chip vendor that wanted Cloudflare's business suddenly found the resources inside their compiler teams to teach people how to be Go compiler writers. And as it turns out, hundreds of patches later, there is a lot of work actually in flight right now, which should result in a Go 1.11. Basically 2 years after fixing that bug that made it not work at all, to get it to speed. Never underestimate the power of a good, well-researched comparative benchmark to light a fire in a routine. Because if you tell these people who are very proud of their new system that it sucks because their compilers are bad, then that's something that they can fix. So that's a success story in progress. So what's the state of the art of ARM hardware? So going from data center grade down, there's new systems on the way from Cavium. The Thunder X2 is on its way. The Qualcomm Centriq is supposed to ship in quantity as soon as they figure out their OEM situation. And there's a new vendor, Ampere, that has the old XG IP out of Applied Micro. They're all promising systems in Q2, probably Q3, maybe Q4 of this year. That will be at least twice as fast as the first generation Thunder X stuff. There's a steady stream of sub-$100 single board computers from the competitors to the Raspberry Pi who don't sell 18 million units, but are shaped about the same, have different chips on them. Rock chip, the Qualcomm Dragon board, NXP has a new unit out. The old BeagleBone, which is slower but still really cheap and really interesting because of other things on the board. Pine 64, just a bunch of interesting little systems that fit in your hand and don't break the budget. On the laptop front, Qualcomm is working with some vendors to do a Windows laptop, so you can run Windows on ARM. Again, it's not important to be very fast yet, but that's just a simple matter of recompiling some software. And several people in this room have bolted together clusters out of the individual ARM-based boards to run Docker and Kubernetes and whatever else to help. What's missing? There's not really a developer workstation out there in the sense of something with 8 gigabytes or 16 gigabytes of memory and that fits in a PC case and looks like a developer workstation. The closest one is a 24-core machine from a Japanese joint venture called Syncwacer or maybe Socionext. There's 24 relatively slow cores. So if you're compiling something, it goes fast until the next step happens and then it just sort of chugs along. So we'll see what the evolution of that is. And the other thing that's really missing is these single board computer designs are mostly repurposed from cell phone designs in some way. And they almost always are relatively slow in memory, 4 gigabytes or less. So they're hard to use as full-blown development machines because your compilers compile just fine, they just blow up at the next step. So state of the art, again, it's better than it was before. Of course, Intel machines are better than they were before. So the world is moving forward. It's just a lot. There's a huge range of parts that you could possibly build something from. And anything from $5, $7, $10 parts up to like $250 parts. Each of which is a little bit different, most of which suffer from the curse of firmware, which I'll get to a little bit more. State-of-the-art software, I've already talked about this a little bit, but basically most things just work. Most of the things that work have binaries available for them. The optimization front is kind of a weak story right now. It's getting better, but if you talk to people who are doing development work, they say, yeah, our hash routines are really slow, or our crypto routines are really slow. The chips can support that, but the software doesn't yet. Embedded systems. Has anyone ever done embedded systems development and is proud of their effort to write firmware? Good, I got the right road. The trouble, this is the Internet of Shit. There's actually a Twitter feed called Internet of Shit, which is just wonderful because it's all of the designs that you can do where you have a part that costs $1 or less and just enough smarts to put it on the internet. And you can embed the internet into all sorts of things that should have never had the internet anywhere near them. So this particular Internet of Shit device is a potty training thing that someone put together. It's a Amazon dash button wired up to a DHCP server, wired up to Twilio, that makes a phone call. So if the kid needs to use a bathroom in the middle of the night, they can just hit the little button and pop over their phone call. In some sense, it's brilliant, but come on, guys, okay? So the low end of the ARM market is full of parts that are very small, very low power, can do just enough to do one thing, lend themselves to being programmed with firmware that can't be updated, that at the worst you get things like IP cameras that get taken over by botnets and software that can never be updated, or if it's updated by the people who are creating. So it's, it's at best it's disposable and unrepairable, and at worst it's a very big attack surface. And so that's also part of the legacy of ARM, is that when compute gets really, really cheap, people use it everywhere. I hit that one already. Just a couple things. One of the other things that's weird about these many core systems, you don't see it in small systems so much, but in systems that have lots and lots of cores, is that they often have strange memory architectures. Rather than having one great big flat memory system where fetching memory from any location takes about the same amount of time, instead they have something called NUMA, non-uniform memory access. And this is actually a chip design from AMD. This is their EPIC, but it's bad everywhere. Not bad, it's just different. So you have to be aware when you're writing things like schedulers or doing orchestration that memory in one memory bank and a processor in another processor bank might be logically close to each other and fast, or might be logically far away from each other. The worst case scenario is people doing virtualization, where they accidentally put cores from two different NUMA domains into the same VM. And so they're trying to virtualize across something where one half of the system is far away from the other half, and it goes really slow. So schedulers need to be aware, virtualizers need to be aware. Mostly this is, again, just a matter of getting enough hardware into enough people's hands. But it's real issues. The other big challenge is build systems. So if you're building for Intel architectures, you can use Travis, you can use Circle out of GitHub, you can create your little binaries and be done with it. If you're writing code in Go, Go is tremendous because it has a cross-compiler that just works. So if you need to generate binaries, you can generate binaries for whatever system Go supports, and it just works just fine. However, if you need to emulate ARM on an x86 machine in order to build what you're doing, you're looking at a 80 or 90% performance penalty. The things only go a fifth of as fast as they would go. So our challenge at Packet, with ARM's help, is to try to figure out how to get as much build hardware in people's hands, native build hardware in people's hands, so that they can build their stuff faster. So that's kind of a state of the art for where things are. Bringing up an ARM system is always there's always one more challenge. They're not perfect. When they work really well. Lots of cores is a really interesting environment to be in. Once you've had 96 cores to compile, you never want to go back to a 4-core system. But so what's happening? What's happening is that ARM is moving up in the market, where the top end ARM designs are trying to attack the data center world, where things aren't. In the middle of the market, single board computers, the things that you can get for $100 or less, have basically, they haven't taken over from office desktops. They haven't taken over from laptops. But if you want to hack on a $100 project, they're the only obvious thing to do. It's a really tough slog in the data center. The number of people who are patient enough and who have enough control over all the software that they run and enough skill to fix all the bugs and to optimize all the things is not all that enormous. So it's going to be hard for ARM to break into that market just on a software basis. And the year of Linux on the desktop is still next year or maybe as it always is. The cool thing about ARM is that, as I said before, ARM is moving its way up through the market. So there's challenges at the top end of the market. What's coming at the bottom of the market, now the way that ARM makes its money is by licensing IP. So you have a core that's a CPU or neural processing unit or whatever, and you put it in your design and ARM gets some money every time you make a chip. Well, you're trying to make billions of chips. What if you could do that for nothing instead of having to pay someone a tax on the chip? So there's a new design called RISC-V. It's a license, it's a openly available IP for cores, really designed to address the same kind of low power, low energy usage, simple reduced instruction set design. There are dev boards for RISC-V. You can boot Fedora on a dev board for RISC-V. RISC-V dev board will set you back $1,000 for a part that really shouldn't cost $100 because it's still in that really early stage. The board itself has a bunch of connectors for your probe tools so that you can pull signals off of it to see that everything is working. But you know, time will come along where the bottom of the ARM world, the thing where they make a lot of their money on, the very low power, low cost chips, where RISC-V has a competitive advantage because it does roughly the same task, but instead of having to buy it from someone, you can just use it for free. Free is good. So,
and those are ARM also, right?
Those are ARM.
Okay, so I'll need to wait for distro makers to port to that also. Right?
Yeah, so the Fedora folks have ported to RISC-V.
Okay.
So the first dev boards for RISC-V, they have a port for. There's a QEMU emulator for RISC-V, so you can run it on your Intel machine or whatever. Yes, porting is going to be, you know, the whole trajectory of 64-bit ARM is probably a 6-year trajectory from the start till now, where you start out on emulation and you slowly build things that can compile, that can be targets, and then you slowly build things that can be compiled into perils, and then you move up from there. So this is, you know, really new. The consortium behind this has a lot of the vendors who are currently ARM licensees. NVIDIA is on board, Qualcomm is on board. So conceptually, it could be the same people making the parts, except instead of putting an ARM core in, they can replace it with a RISC-V core. But it's going to take time. These software things are measured in large parts of a decade. I feel kind of lucky because my remaining career is measured in, you know, a decade plus, but it's not like 5 decades. So I think as long as I stick with the ARM world, I'm doing okay. And the RISC-V people might eat my lunch, but I was putting them on the slides 7 years before they do. It's a challenge. The world that I'm in at Packet tries to be really agnostic about hardware. We love hardware. Right? We want software people to have as many choices in hardware as they can to put their stuff on. And so ARM is only one of the things that we do. It's about 3% of our data center. And coincidentally, about 3% of our staff. So it's not enormous, and I do other things there more than just work on ARM stuff. But yeah, I mean, I think there's two futures, right? Future one is more and more high-end 40 to 200 core or 40 to 200 thread systems poking into the data center and doing something over there. And then the other thing is that at the bottom end, RISC-V designs with very low cost breaking into the embedded world. And I'm not even going to guess how many years it'll take for RISC-V to make it. Right? That might be just to get iterations of quantity, iterations of quality.
So what you've seen with ARM, what do you think would actually take to accelerate that?
Well, so one of the things that has made it difficult in the ARM world is just how fragmented it was. If you look at it 2 years ago, there were a bunch of essentially independent efforts. Right, the licensees, the ARM licensees are all independent companies. They compete with each other. So it takes a lot of work to push them into a space that lets them cooperate. And ARM Inc. as an organization is okay at getting that cooperation from their licensees, but they're basically arms dealers, right? They're selling stuff to these people to get them to compete. With RISC-V, the consortium model is really different. There's one consortium that everyone belongs to. There's still competition, but it's really competing for shared interests more so than not. So I think it will go faster by nature. And also, once you've been through one revolution of a system like this, you kind of understand what the next thing's going to be. Right? If I was gonna have this talk be a farewell to ARMS, right? So I'm not going to touch the ARM system ever again. I'm just going to go RISC-V always. The first thing I would do would be to optimize your code. Because if you can get your code to run fast, then you need less chip to do it. And I do containers on RISC-V, sure, I do orchestration.
So is the RISC-V, is that anything at all based on the old style RISC chips? Or is it just similar in name?
It's based on the old style RISC chips. The two guys, Hennessy and Patterson, who did a series of computer architecture books, are both on the board of this. Hennessy went on to be president of Stanford, I think. They both work at Google now. It basically has a heritage of this RISC systems.
Okay. So that will help.
That will help.
Because there's a lot of legacy stuff out there that would run it.
Well, it's a different chipset and a different everything.
Right.
But just the knowledge of how reduced instruction set computers work. Yeah. And I think they have an advantage because they're starting from a green field. Right? They don't have to worry about legacy systems. They don't have to worry about compatibility. They don't have to worry about upsetting some part of their existing market. They can just start from scratch. But I think you'll probably see RISC-V designs not in Raspberry Pi shaped things for a couple of years. At least not at that price point. Price point of the they're selling development boards for it, essentially. But it's a $1,000 development board. It's a couple turns of the cycle to get that down to a $150 development board. And it's a couple more turns to get it down to a $35 development board. You might not even want it.
I'll be there.
It's good hobby in your retirement.
Sure.
So that's what I got. Any more questions?
I've got tons of questions.
Okay.
So I see the centric, I don't know how
Yes.
it's pronounced. The 2434 is an $888 chip compared to the first Xeon, which is like $2,500.
Right.
Like generally speaking, for like a 1U, just like a small server or whatever, is it about equivalent mean, the Xeon only has 12 cores. Like generally speaking, like is it like a power machine where if I put you on a power machine, you wouldn't be able to tell unless you actually looked?
Yeah.
Right.
So the equivalence that people are aiming for in terms of performance
Right.
is not per core performance.
Right.
It's per socket performance.
Okay.
So if you look at one socket machines, the top end of the Qualcomm line matches pretty nicely with the Xeon.
Okay.
It's not the individual cores, the 40 to 48 cores that you have. Actually, we had an early spin of the silicon, a machine that had 47 cores. It was the fastest 47. I don't know how to do 47. The individual cores don't run quite as fast, but you can get total system performance. I mean, really, it depends. It's back to Amdahl's law. If your core is too small, it doesn't matter how many of them you have, because you're spread too thin, and you get stuck on serial performance. If your cores are fast enough to handle the serial stuff, then you pack more of them into the same.
Right, because they're not. I mean, they're 2.3 gigahertz. I mean, obviously, an IPC is different per member, but like,
that's not slow.
yeah. I mean, is it okay?
Yeah, these are peppered machines,
Right.
Right. You notice what you notice is what you notice first, and this depends on the machines, is that you have to tune a little bit to figure out how many jobs you're going to run at the same time. If you have the whole machine to yourself, which you will for some short amount of time until it gets used out, then you just run with however many cores, do all of them, and you discover this slow linker stuff. The people who are doing big development jobs, like if you're compiling things, and you want to compile all 2,000 packages in your package database, you typically don't serialize that, you parallelize that by saying, every job gets 2 cores, every job gets 4 cores.
Right. Okay. Are there any like ARM chips that sort of do also you see the cell phone or something that just for like you have a couple cores that can like higher speeds, whatever you call it, or whatever.
Yeah, so the data center stuff doesn't tend to have big little type designs. They tend to have all of the cores the same. And I think that's mostly a cost savings. Qualcomm especially doesn't have any 32-bit execution in their Century chip. It's a 64-bit only. Cavium is 64-bit only. The Ampere is going to be 64-bit only.
Yeah, they boost a little bit, but not like 2.3 to 2.5. It's not like Intel. It's like this huge.
Yeah, and some of these things have really interesting, like I mentioned, non-uniform memory architectures, but basically when you get lots of cores, you have to architect essentially an internal structure of some sort.
cache placement.
Yeah. Caching becomes really important. Yeah.
Is there like so you were talking about the LoRa one, so I have like a Raspberry Pi.
Right.
Let's say I want like a home server with a little bit more beef, but the Centric is obviously, is there like a 250 to 500?
There's really not much above. So right now, if you were going to spend $250, you could get a top of the line. Marvell has a system that's the Macchiato bin. It's kind of a bigger board, a little bit bigger than the Pi. The thing you're going to pay more for is a device that lets you put more memory on the machine.
Okay.
Because the single board computers are almost always capped at 4 gigabytes. I think I saw one design at 6, but they're basically 4 gig machines. So if you want something that has separate slots for memory, you go off into another domain. It doesn't have very many things in it. And then if you really are willing to spend $1,200 on a kit, this 24-core machine would be an interesting one to have. I don't know that you'd be happy with it every day, but some days you'd be happy.
What's the vector capabilities of these batteries? pay much attention to that.
You have to think of it as a heritage from cell phones. So a lot of designs have a GPU on them. Often the GPU isn't the software to run it isn't very open. A lot of these things have closed binary blob type stuff just for graphics acceleration and whatnot. The ARMv8 chipset has some instructions that let you do like parallel adds or parallel multiplies.
Yep. How wide is that?
I don't actually know. I don't think it's as wide as the widest Intel stuff.
Oh yeah.
But it's wide enough to make a difference in accelerating a lot of that.
Maybe for operations. Or for you.
Like 128 bit, I think is easy to get. There might be some 256-bit instructions.
So with 128, you're at 64-bit.
Right.
Pretty limited. Still, that's better than not having.
Right. So there's also some instructions. The fun thing about ARM is that if you're designing a processor and you want another or you don't want an instruction in it, you're perfectly within your rights to not include it. Because you're making a chip, you've licensed it, you can remove things, or you can add stuff. So there's a series of ARM specifications that usually come out every year or so, describing the latest and greatest ARMv8.1, ARMv8.2.3.4. And so as the instruction set evolves, it's tending to evolve towards having a richer set of wider instructions.
I can see in the future, tuning the chipset to HPC environments.
Yeah. So one of the vendors of ARM-based systems is Cray. Cray uses the Thunder X2 hardware with its own hardware design and its own optimizing compilers and its own Fortran and its own. And they did a benchmark against meteorological codes from the UK, and we're really happy with the results. Like, in whatever limited domain they were in, like not the domain of all the software in the world, but the domain of those codes, they ran without incident because Cray had done a good enough job at the compilers. But you can't get a Cray compiler for your compiler. So sometimes the advances in compiler technology are tightly coupled to the vendor.
Right. You mentioned the other slide's LLVM.
Yes.
What's that like? Is it catching up to GCC, or is it surpassing in the ARM world?
In the ARM world, there's a bigger set of people working on LLVM than GCC. It seems to be better funded. I know that the FreeBSD folks just rebuilt their whole system with LLVM just to see how it would work. The linkers are faster. The link step that I mentioned being the slow, frustrating part, they did more parallelization of the linking step. So that goes speedier.
For most, you just need to do it once and you run the code forever after that. But
well, for some people, you run it once and compile once and run the code forever. For some other set of workloads, all you ever do is compile.
Sure.
And you run your tests and then you discard them and then you run the next one. So it depends. That's what I got. One more question.
Yeah, so if you had a large-scale ARM cluster for whatever workload, what operating system would you run on? And why is it CentOS?
And why isn't it CentOS? So we've got choices. You've got choices. Ubuntu is from a corporate. So there might be a bunch of different reasons to run Ubuntu. right? So from a corporate health perspective, Red Hat is a healthier company by a lot. They're healthy because they are a lot healthier because they're making more money.
Yeah.
Right? So that would be one consideration. If you're going to run this thing for a long time and you want a long-term vendor, you want a long-term support, that would be one thing. Ubuntu, I think, has had a bigger track record just in terms of everyone brings up Ubuntu. The first thing Ubuntu will run on really, especially Debian, will run on really weird systems. Whereas CentOS to a certain degree, Fedora not so much. Fedora will try to run it. But Red Hat, as a matter of corporate policy, have made it very hard to get a certified version of Red Hat on ARM hardware, unless the ARM hardware supports the standardization of servers. And this is a long-running religious war. It's not a technical thing.
So cannot with Capu,
Right.
so there's like significantly more practice.
Yeah, back then we co-launched Linaro with ARM. It's like way back in the day. Forgot the one in Texas was one of the ARM server startups. We spent a lot of money. What they would call there.
Was that XG?
No,
AMD? Optron.
no, it was.
I don't know all the back.
I'll yell it out if I remember.
Yeah.
It doesn't matter now, right? Does it?
So I kind of said it as a joke, but it is actually a fair question. What would you run regardless of the?
So what we do at Packet is we spend a fair amount of time maximizing the amount of choice that people have when they spin up a machine. So that if you get tired of running Ubuntu one day, you spin it down and spin it up again. Your operating system in the right sentence. Right, just optimizing the ability to make a change without it being a process.
Right.
So that's one direction. Like, we'll run whatever you want. If you get tired of it, run something else. If you were to run a big system over a long period of time, I would probably right now be targeting on 1804 Ubuntu, just because it'll take a little while to get there. That 1604 is going to look long too. You probably want to replace your Go compiler every time you Go compiler comes out, because the latest Go compiler is always the best one ever. You want to, the operating system matters less and less if you are always running current software. And we've been, so one of the places that Packet is making an investment in operating systems was actually with Alpine. We use Alpine as our rescue operating system. So every single machine, when it boots into Alpine. When it gets stuck and somebody needs to rescue it boots into an Alpine memory. When we turn it off and scrub it for the next person, it goes into Alpine. So we depend on Alpine.
Do you see you building some like Linux kit or something like that built specifically for?
Yeah, so the Docker folks have been working really hard to make Linux kit compatible between ARM and x86. Microkernels are awesome. Unikernels are even more awesome. It's a matter of buying into a whole world of doing things a certain way. I think containers make the operating system less important. Like, I would rather be in the container world than the operating system world right now.
I agree.
And you know, that's going to play out again over a long period. The other thing that's a wild card to me right now is that we signed a cloud services agreement with SUSE to run both SUSE and OpenSUSE in our systems. I've never used those things. They sound interesting. They're stable. Sure, why not?
Zipper.
Yeah, you know, like, oh, like whatever. So, good. Cool. Good. Thank you very much. Should I disconnect from the Hangout?
Sure. Are there any other questions or anything? Otherwise, I think so.
Okay.
See, one thing I like about ARM, it's like a lot of these boards, even if they're